In this video, we'll generate the dataset of the geometric series of 1 minus x to the power n plus 1 over 1 minus x. And we'll use Taylor-Maclaurin series sum to generate the expansion. And we'll also use the LINEST Polynomial Regression to generate the regression coefficients. We begin with the values of n, which is data validation, list of items 0 to 8. And we'll use array formula to generate the data set. So array formula of 1 minus x to the power n plus 1, n plus 1 all over 1 minus x. Third, and we chart this. We use the scatter chart. And draw the trend line, and it should be polynomial to the 8th degree. Use this equation. Put it on the left side. Here you have the trend line and the trend line equation, or the trend line polynomial of the geometric series. So we have n equals 1, so n equals 2, 3, and 4. Next, we use the Taylor-Maclaurin series sum to generate the expansion. So it is the summation of a times x to the power n, k, where the value of k is from 0 to n. So this is equal to sequence n plus 1, one column starting from 0, incremented of 1. So if we have n equals 3, that's 1, 2, 3. N equals 4, 1, 2, 3, 4. Next, we generate the Taylor-Maclaurin series sum. So array formula, series sum of the x values raised to the power, starting from 0, incremented by 1, and the coefficient will be this range. And this will be 1 if, so this is array formula. If k is empty, if it's empty, then 0, otherwise it's 1. So if k is empty, it is 1. It is 1 if k is not empty. So here we have the dataset of the Taylor-Maclaurin series expansion that match to the geometric series. Next, we use the LINEST Polynomial Regression to calculate these coefficients. So here we have array formula of the x values to the power 0 to 8, because we generated a trend line to the 8th degree. So now we can use LINEST data y and data x. Likewise, in the Taylor-Maclaurin series sum, which is LINEST data y and dot x. So start from 0 and we generate the trend line. Series trend line polynomial to the 8th degree and show the equation. Here we have the equation. So at n equals 0, our equation will be y equals 1. Y equals 1. N equals 1. Y equals 1 plus x. So 1 plus x. And at n equals 2, our polynomial is 1 plus 1x plus x squared. That's 1 plus 1x plus x squared. 1 plus 1x plus x squared. At n equals 3, our polynomial is 1 plus 1x plus x squared plus x cubed. 1 plus 1x plus x squared plus x cubed. Same thing with this, the Taylor-Maclaurin series expansion. X equals 4, n equals 4. Our polynomial is 1 plus x squared plus x cubed plus x to the fourth. Same thing with this, 1 plus x squared plus x cubed plus x to the fourth. And at x equals 5, a polynomial is 1 plus x squared plus x cubed plus x fourth plus x to the fifth. 1 plus x squared plus x cubed x fourth x to the fifth. At n equals 6. So our polynomial will be 1 plus x squared plus x cubed plus x to the fourth, x to the fifth, x to the sixth. Same thing to this, 1 plus x squared plus x squared, x cubed plus x to the fourth, x to the fifth, x to the sixth. And at n equals 7, our polynomial is 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth, x to the sixth, x to the seventh. Same thing with this, 1 plus x squared plus x cubed plus x fourth plus x to the fifth plus x to the sixth plus x to the seventh. I think our expansion coefficient also match. And at x equals 8, so regression coefficient match to the expansion coefficient, and our polynomial will be 1 plus x squared plus x cubed plus x to the fourth, x to the fifth, x to the sixth, x to the seventh, and x to the eighth. This completes the use of Taylor-Maclaurin series sum and LINEST polynomial regression to generate the trend line and the dataset of the geometric series.